a table, or some of you knew, okay, start at 3 on the y-axis, follow the slope, -2/1, so you went down 2/1, down 2/1, down 2/1 to get your points. Probably just made a table for this. Probably just made a table for this, although absolute value 1 is 1, 2 is 2, same thing for -2. Most of you recognize or identify the V shape from algebra 2. When you get to the bottom, we're doing the same graphs, except they're being restricted for x values from -3 to +2. Okay, and this one doesn't have equality, this one does. I'm just writing on there. It's not really part of my graph, I'm just making a note of this one's going to have an open circle, this one's going to have a closed circle. And all right, so here we go. So on this one, at 0, I have 3 still. And then I go up 2/1, up 2/1. Oh, that's not up 2, up 2/1. And one last up 2/1, but I have to put an open circle there. So the graph before, on the graph above, it kept going up infinitely. You can see that's indicated by the arrow here. But down here, it has a specific starting or stopping point. If you're going from left to right, it would be its starting point. And then I'm going to go all the way down to 2, so I go down to, down 2/1, down 2/1, and that is a solid dot at 2, -1. Again, if you wanted, you could get your table from your calculator if you put the functions in. For mine, I put it in for y(1). So I could go here and I could actually input the values. -3, -2, 1, 0, 1, 2. And those would be my, in column y(1) would be my x answers, or my y answers, my heights. For the second graph, it says x is greater than or equal to -2, so I will have a solid dot for that. I'm going to make a note of that. And on my graphing calculator, I'm going to go to that function, which I have it in as y(2) equals 2x². So I go to the table, and now I'm going to change my x values to be everything greater than or equal to -2. So really, I can just get rid of my -3 one. So now I'm looking at the y(2) column. My first point is -2, 8. -2, 8. I'm going to have a solid dot there. My next point is 1, 2. My next point is 0, 0, and then 1, 2. Negative, or 2, 8, and then 3, 18, so we'll just do the 2, 8. Okay. Now the difference on this graph is I have a solid circle here indicating that it starts or stops there. And then from there, I'm going to connect the other points, but it doesn't really have a maximum. The maximum is there is no maximum. It's not unbounded. So I do have to put an arrow on that side indicating that the graph continues going to the right and continues going up. Any questions on that one? All right, and for our last one, from -1 to -3. So in my calculator, I put this in as my y(3), and I'm supposed to do this from -1 to +3. So I'm going to put this in as -1. And there we have the table. But now I need to go to my y(3) column. So my first point is -1, -1, then 0, 0. 1, 0, 0. And then I have 1, -1, 2, -2, and 3, -3. Now I have to note on this that I'm going to have an open circle at both of those, at -1 and at 3. So where my x is -1, this should be an open circle, this should be an open circle, and the rest of the graph is connected as normal. So I only have a piece of the overall function. Any questions on that? All right, so what we're looking at today is piecewise functions, putting functions together that for part of the domain, the graph behaves a certain way. In real world data, you might have graphs that do some crazy things. Maybe initially it follows one model and then it does something crazy, or it does something like this. And so to describe it, we may need to use a piecewise function that has, part of one function fits this data and describes it well, and then another function might fit it up to here, and then a linear function here. And so we'd also have to define, well, where does that start and stop? Where does each piece start and stop? And here is that, they kind of gave that to you up here, where you're going to start and stop these pieces. So today we're going to look at, or start looking at piecewise functions. But, so in this piecewise function, we actually have two pieces of a graph. We have to be really careful around the points where one stops and the other one starts. And tomorrow we're going to be looking at some graphs and seeing that we need to be careful when we're describing what's happening to the graphs. So basically for this graph, there is no lower bound on this equation. There's just an upper bound, a maximum value on this equation, and that's at -1. That's where our graph is going to change from one equation to another one, because it changes from one curve to another. So we've got an open circle for this particular graph, piece of the graph. And then for x is greater than or equal to 1, again, no maximum for this one, but a minimum for this one. And it is going to be a closed circle because it does have equality. So we're going to start with, and you can make a table if you want, or you can use the linear function. Since this is a linear function that starts at -2, I'm just going to follow the slope for that function that I have more highlighted in red. I have start at -2 on the y-axis, and then I'm going to, that's the y-intercept. And then I'm going to follow the slope of -1/2. Slope is -1/2. It might be easier to make a table. We can do it that way too. So in my calculator, I'm going to clear the function, just because we're doing pieces and we want to have a specific starting value or a specific stopping value. So in y(1), I'll put in -x over 2 minus 2. And I can go to my table. My minimum or my maximum value is -1. So I need to start at like -10 or -8, -6, -5. I'm not worried because it's linear, so if I have some of them, I'm good. Not -5, I wanted, -4, -2. I do want the specific value for -1. Because that's an important one. So at -8 on the x-axis, I have a corresponding y value, so I'm going to show my table here. We've got -8(2), -6(1), -4(0), -2, and -1. -2 is -1, -1 is -1.5. So I'm going to plot those points. This is my x and y value. I'm also going to make a note in my table that at -1 I have to have an open circle, so I don't mess that up and put it as a solid dot. So -8(2), -6(1), -4(0), -2, -1, and -1, -1.5 as an open circle, and that doesn't look very good. That doesn't have a minimum. It's unrestricted. It goes to the left and up forever. So I make sure to put an arrow on it indicating that it does that. If it did have a minimum, I better not put an arrow on it. I better have a specific point that it stops at. For my second piece, I have the absolute value of 2x plus 1, which I could make a table real quick in my head, but I'm just going to look at the calculator anyhow just to make sure you're familiar with how to use it. So this is our x, and then here's our y value. In y equals, I'm going to go to y equals, and I'm going to clear it, and I'm going to go to math, number, absolute value, 2x, and outside of the absolute value symbol, plus 1. And this is from -1 up. So I need to make sure to include -1 and 0 and 1. And then I might just do 3, 5, 7, because we know it's going to have a linear type behavior. We already see the bend there. So here I have -1, 3. So -1, 3, 0, 1. 1, 3, 3, 7. 5, 11, which isn't going to fit on our graph, so we're good. All right, so -1 on the x-axis, I go up to 3, and this one, because of the equality, I'm going to have a solid dot. So I make a note even in my table, so I remember to put the solid dot there. Because of this inequality, x is greater than or equal to -1. So -1, 3, I put a solid dot. Then I have 0, 1 as a point, 1, 3 as a point. It's not working very well. 3, 7 as a point. And 5, 11, which I'm not going to fit on. So it comes down, and then it goes back up. And it doesn't have a maximum value, so I'm going to put an arrow on it as well. Questions so far? All right, so now I've graphed them. Now it asks me to state the domain and range. So sometimes we fold our paper, or at least before we folded our paper sideways in from this side and in from this side to look and see what were the maximum values. Do I have an absolute minimum value, like the smallest value for x? No, right? Because it keeps going on infinitely. So my absolute minimum value is -infinity. And do I have an absolute maximum value where it doesn't stop, it just keeps going to the right, right? So that's going to be positive infinity. Now the only other thing I have to check for is that there are no breaks or gaps in the graph when I'm looking at the x values, kind of like the vertical line test. Not to tell that it's a function, but to make sure that every vertical line I look at has a point sitting on it. So -10 has an output, -9 has an output. All of these have outputs. We have a problem right here. But is there an output for -1? Yes or no? Yes. Up here, there's an output for it. Now, if that were an open circle, that would break up my domain. I would have an interruption in my domain, and I have to account for it. But it's not. It's a solid circle, so even -1 has an output. All of these x values that I look at have outputs. So, since I have no minimum value and no absolute maximum value and no interruptions in the graph in between, the domain for this first piecewise function is -infinity to +infinity, or all real numbers. The range will be a little bit different. Does the range have an absolute minimum? What's the very lowest point we have on this graph? -1.5. And look, my graph's kind of cruddy, but you can see it from your table right here. And it doesn't have equality with that point, right? Right there, -1.5 is our absolute minimum on our range. So we need to be aware of that. And then as I travel up, this goes up infinitely, so I don't have any other gaps. This is going to keep rising. I don't even really need to look at this other part. If it stopped over here somewhere, then I'd have to look at the other part and make sure all the y values are covered, that for every y that I could think of or see, that there would be an output somewhere on the graph. Sometimes there's more than one output. You can see there's 1, 2, 3 for that, and that's okay. They're different x values. But there's that height. At 3, there's 3 points that have a height of 3. So our range does have an absolute minimum, and that's at -1.5. Notice I didn't use a bracket because it can't have equality with it. And it can go up infinitely. There's not a single point missing above it. So it can go up infinitely. So there's our domain and range for that piecewise function. Take a look at letter B. This one, unfortunately, has 3 pieces. 2 of them are pretty basic, but the other one's not. So the The first one's not, so we'll pull out our calculators real quick. And we'll do the opposite of x plus 4 squared. Some of you already know where the vertex is because this is in vertex form. If not, we'll be reviewing that eventually. So that range, that also doesn't have a minimum value. There's no min. It does have a maximum value on this piece at -4, and it has equality. So when I make my table for this particular piece, okay, we may have to switch modes. When I make my table for this particular piece, I'm going to end my table at -4, and I'm going to make sure to have a closed circle there when I go to graph it. So let's put this in the calculator. We've got, let's do -8, -6, -4. Should probably do -10 too, but can't get -8 anyhow. I better do -5 because this one is a quadratic and it's going to change behavior in there, which we probably already predicted. So on this table, we've got -6, -2, -5, 1, and -4, 2. This was a 2, and -4, 2. So I'm going to plot this in black. -6, +2. No, was it positive or negative? It was negative, right? Thank you. I just wrote the wrong thing down for both of those. So now we've got -6, -2, -5, -1, and -4, -2. And at -4, -2, I'm going to put a solid circle so that I know that it has equality there. I'll connect these, and since it has no minimum, it's going to continue this parabola type shape infinitely as it goes to the left and down. So that's our first piece. Our second piece might look a little strange. This is, remember, it's f of x, so that's y equals, you see the f of x equals 4, which means the output is always 4 from -4 all the way up to 2. Okay? Neither one of those have equality, so I'm going to have to do open circles at -4 and at 2. But my output for every point between them, my height, will be +4 for every point between them. Okay, so then I go to -4. I go up to a height of 4 and put an open circle. I go to +2 on the x-axis. I go up to 4, put an open circle, and then I connect those two with a line showing that every point between those has a height of 4. So that's just a flat line plateau. That had a maximum and a minimum for that piece. Now our next piece is a linear function. Probably could graph it without a table, but I'm going to grab a table anyhow. 3x minus 15, and the y equals 3x minus 15. And that's from a minimum value, bless you, of 2. So this is our minimum, and it has equality, so it's a solid circle. So for this one, I'm going to start at 2. I'm going to make sure to graph a solid circle. And it's linear, so I'll do 2, 4, 6, and 8. And I'll be able to graph from that. So I go 2. Did I put the function? Yes. Second table 2, 4, 6, 8. We have -3, or sorry, -9, -3, 3, and 9. -9, -3, 3, and 9. So we go to 2, -9, and we put a solid circle. We go to 4, -3, and we put a point. 6, 3, put a point, and 8, 9, put a point, and connect our graph. This is the minimum, so I'm not going to go to the left of it, but it had no maximum, so it keeps going to the right and up. Any questions on graphing or making the tables for piecewise functions? All right, so with these 3 pieces, I now have to evaluate my domain and range. I'm going to look at my domain in green. I have no absolute minimum. This graph keeps shooting to the left infinitely. So it goes in a negative direction infinitely. And on the right side, I have no absolute maximum. It keeps shooting to the right infinitely. So when I'm considering my domain and range, I know that at least part of those intervals that I write, one of them is going to have this, one of them is going to have the negative infinity, one of them is going to have positive infinity. Now I just check every x between. Where's the only place when you look at this graph that there might be a problem? What x values might have a problem? Even just looking at this table, what x values might have a problem? X equals 2 and x equals -4, right? Because this is where they split. So I just have to make sure that there's actually an output there, because I know the rest of these functions work, that the graphs keep going. So right here I have, it's missing an output at -4, but that output ends up being filled in down here, so that's okay. That's what we call a jump, just for the record, because that's going to be important later. It's a jump in the graph. It's where it jumps from one height to another. Even if it doesn't take on the value, it jumps to start a new piece. And then the same thing here. There's no value here, but it's okay because even though we don't have a value, a height for 2 on the red graph, we do have a height for 2 on the blue graph, or on this linear part, this linear piece. So because of that, it's okay. I don't have any missing x values in my domain. And all the other ones you can see are connected, so we have that. So once again, it's not always going to work out this way, but for this one, our domain is from negative infinity to positive infinity. There are no missing values of x or any values of x that don't have a y coordinate somewhere on the graph. Now I'm going to take a look at the range. As I look at the range, I saw this and thought, uh-oh, do I have an absolute minimum? On that piece I do, but not absolute, because when I look at this, it goes down infinitely on the left, and on the right, on the blue graph, it goes up infinitely. So now my only thing that I have to worry about is, are there any missing y values between? Okay? So I look at this, and as I work my way up, there's always an output. All the way up, there's always an output. The place that I might have been the most concerned about would have been right here where I have these open circles, or even just this jump right here. But I don't have to worry about that because this blue piece took over, and there's a height for every one of those points. Okay, and then even beyond it. So I know that my range, since every y on the y-axis goes over to some piece on the graph, is from negative infinity to positive infinity. It's also all real numbers. Give that a try for letter C. Make your tables for these 3 pieces, see if you can graph it, and we'll talk about the domain and range. All right, so which piece gave you the most problems with graphing? Which one was the most difficult to graph, or which 2 might have been the most difficult to graph?
Over x.
The 2 over x, okay? So we know if we're just looking at that saying, hey, are there any restrictions on that domain? You have a denominator there, right? What do you know about that denominator? Or what do you know because of that denominator that x cannot be? X can't be 0. So that's important to note that even though they're telling us that we have equality right there, right? Oh, you can have 0, right? Well, you can't because of the function that it is. So we're going to make a table of that and take a look at that. But first, let's look at the first function. We have your -2 by absolute value of x +